then U will loop. Right? How can U not loop? Well, if it accepts or rejects. If U does not accept and does not reject, well then it loops by definition. That's the only other possibility. It's only three things it can do, right? So if AMW loops, if it does not accept and does not reject, well then similarly U will do the same. It too will loop. Okay. Now, that's why this Turing machine U, it's not a decider. It's not a decider because there is a possibility that it loops, and U can loop if M loops on W. So there is a possibility. There's definitely a possibility that M can loop, and then if M can loop, well then U can loop, and if U can loop, then by definition, it's not a decider, right? Okay. Now, if we could have U somehow, the algorithm, if somehow we could determine that M is not going to halt, in other words, it's going to loop. So if there was some way that you could know that M was not going to halt, that if there was put another way, rephrasing it, if you could know that M was going to loop, well then you could have U rejecting, right? Because looping is not accepting. If you're looping, you're not accepting. But well, there's no way that you can know that M is not that M will loop. There's just no way of doing that. And now this language now is it tends to be called the halting problem, because there's just no way that you can determine that your M is going to loop or not. You just don't know, right? And that's what's called the halting problem, because you're just in ignorance of what M is going to do. Because if you did know what M was going to do, whether it was going to halt or not, then you could have U, which is simulating M. So if you can determine that M's going to loop, well then you have U reject, and that would then make U a decider, and therefore the language ATM would then be decidable. Okay, but there's no way we can determine whether M will loop on the string W, right? So we've got a problem. We can't do that. So we cannot create a Turing machine that decides this language. That inability to decide the language, that's called the halting problem, right? Famous halting problem. All right. Now this Turing machine, U for universal, with comment by Sipser. He said, it's interesting in its own right. Well, it sure is. In fact, I'm feeling rather antsy that he devoted so little attention to it. He just skipped over it, which is a pity because it's fascinating, and it played such a major historical role in stimulating people, especially engineers, logicians, and so forth, with a engineering turn of mind, including Turing himself, to actually design more practical versions of Turing machines that would be they have stored programs and would be universal, and that you could get them to program anything that you programmed into them. Right, so Now this Turing machine U, it's an example of what Turing called well, he didn't call it himself, what's called now a universal Turing machine, a UTM. It's a very common abbreviation in theory of computation, and it was first proposed by Turing. Now you can probably see the first line here, but I'll crib a little into the next session. Now the reason why that Turing machine U is called a universal Turing machine, a UTM, is because it's capable of simulating any other Turing machine, or capable of simulating any other Turing machine. Now, and you know, what are we doing? See, so here, so this Turing machine U, it's simulating M. But what's M? Well, M's a Turing machine. So you've got a Turing machine simulating a Turing machine. Okay, and this Turing machine U can simulate any Turing machine M. Okay, so in that sense, it's universal, right? So any given Turing machine with a specific job, let's say, so it's let's call it like a narrow Turing machine. It's a Turing machine that does one job. Well, this Turing machine U can simulate it, but this machine could be any Turing machine doing any job that it does, right? A whole range of different jobs. Each one done by a machine M. But whatever that machine M is, you can simulate it, and hence it's universal, right? It can simulate any Turing machine. Now here's the tragedy, I think. When I got into this board and looked ahead a bit, I was disappointed to realise how little time and energy Sipser is going to devote to the UTM. So I'll have to take it up in other texts. Like I've shown you these two before. They're both on theory of computation. These two texts that you've that I've introduced before. Now the Minsky one here, Computation, Finite and Infinite Machines. He has a whole chapter, I don't know, 15 pages or something, on the universal Turing machine, the UTM, because it's a fascinating story. And I don't know, 5 or so, quite a few pages in this one. Now I'll give courses on both these. Now I'll give you a taste of its fascination and why it's so intriguing. So this Turing machine U, it's taking as input a machine M, okay, on a string W. Well, I'm a bit rusty, and it's not in Sipser, so I didn't refresh myself. But from memory, it was quite a few years back. It goes. If I get the details wrong, it doesn't matter too much, because I'll do a proper course on it, and you can read it up if you're interested. But imagine that your universal machine U is having as input. So its input would be this, but the M here is U. So it's getting input, a description, where this machine here is not a narrow machine, it's a description of itself, right? So this M here is actually U, capital U, right? And well, now you've got a machine talking about itself in a sense. So you get this self-reference, and typically that's when you start getting paradoxes. And Turing himself, after he dreamt up the idea of the UTM, the Universal Turing Machine, he then used that idea to prove that the halting problem cannot be solved. Well, I'll sort of leave you at that. We'll do some of it. You get the kind of paradox that mentioning on the previous board with the Barber paradox. When you start having statements that refer to themselves, kind of recursion, that tends to be when these logical paradoxes arrive. So if you've now got a Turing machine that's simulating itself, well, you can probably sense this scope for paradox, scope for contradictions and logical conundrums and so forth. Right? Turing machine simulating itself. Interesting. All right, I'm just whetting your appetite. Okay. All right. Well, that's the end of the session. So.